All right, so we are starting our notes on page right here. Page 17, thank you. Go to page 17 if you would, okay? So we are going to talk about more with exponential functions, okay? We're just going to keep practicing what we know. So how do you determine if a table of values represents an exponential function? Well, the first thing that you want to check is you want to make sure that your input values, so your inputs or your x values, and put x in parentheses because usually it's an x that we input, but sometimes, like you saw in that last example, the exponent was actually a t, so it's not always x, but you want to make sure that your input values are at regular intervals, meaning 0, 1, 2, 3, like we're counting in a row, okay? And then you want to look for a pattern in the range. We've done this with linear functions, right? We try to find the change in y. Is it constant? If there's a common factor, remember that means a multiplier. If that like change in your range pattern, like if that pattern is you take the last term and you multiply it by something to get the next term and you multiply it by that same thing. If you have a common multiplier, then it's exponential. It's linear if you have a common difference, and that's something that you would add or subtract to get the next term, right? You guys know that. That's your slope, right? You add it or like whatever that value is, that's what you're doing to get to the next term. So we're going to look at each one of these tables, and we're going to determine if they are exponential or linear. And if they're exponential, we want to say what the common ratio is. And if they're linear, we want to say what the common difference is, okay? So first off, if we look at that first table, are the x values like increasing in a incremental order? Yes, okay? So what am I doing here? Well, if it was a linear function, I would be doing plus 2, but that's not what's happening, right? So I know that the linear model doesn't work after I get to the second term. So that means it has to be exponential. So let's check that. 1 times what is 3? 3 times 3 is 9. 9 times 3 is 27. So I know that this is an exponential function. Whoops. And I know that the common ratio, oh, I don't know what is going on. I know that the common ratio, I really don't know why it's doing that. The common ratio is 3. We're multiplying by 3. So I'm going to put times 3. Actually, I'm not even going to put the dot there. Just 3. That's my common ratio. That common ratio, remember, is also called your, what is going down today? It's also called your base. I'm being punked today. Hopefully the next one will work. Okay. So we know that's a base. It's exponential. Let's look at, yeah, you can put common ratio if you want, but the common ratio is the base. So let's look at the next one. Are the x values increasing in an incremental order? Yeah, they're all going up by 1. So now let's look at the y values. Well, if this were linear, to go from 1 to 6, I added 5. And if I were to repeat that pattern, the next term would be 11. It's not linear. So that means it's probably exponential, not necessarily. But to go from 1 to 6, what am I doing? Times 6. 6 times 6 is 36. Oh, that works. 36 times 6 is 216. That works. 216 times 6 is 1,296. So my common ratio, which is also my base, is 6. And we know that this is exponential. You guys take a look at the third table and tell me what you think. Rosie, what are your thoughts? Yeah, you're right. We're multiplying by 1/5. So that means that the common ratio, which is also the base, is 1/5, and it's exponential. What about example or table number 4? We're adding 3, so this is going to be a linear function. And it doesn't have a common ratio. Instead, it has a common difference. And it is plus 3. Good job. All right. So we're going to talk a little bit about an arithmetic sequence and a geometric sequence. I don't want you to get caught up on the terminology. I just want you to use the formula, okay? So an arithmetic sequence, much like a linear function, has each term builds by adding or subtracting another number to it, which is called the common difference. So the recursive formula for a linear function is a to the n plus 1, a sub n plus 1 equals a sub n plus d. Let me explain to you what this means. A sub n plus 1 equals a to the n plus d. We're going to look at this sequence right here. So this is just a set of numbers, 3, 5, 7, 9, 11, and then typically they're represented by a dot, dot, dot instead of the words etc. The first term in my sequence represents a sub 1. That's the first term in the sequence. So the 7 would be a sub 3 because it's the third term. Does that make sense? Yes or no? Okay. So let's say that I wanted to find the term that comes next. I wanted to see what came after the 11. Well, the first thing that I need to do is I need to figure out what that addition or subtraction factor is in between each term. So it looks to me like I'm adding 2 each time, right? Do you guys see that? So my common difference, or D, equals 2. So the recursive formula is a to the n plus 1 equals a to the n plus 2. Now, what does that mean? That means suppose that I want to know what the 7th term is. Well, let's see. I know the 1, 2, 3, 4, 5th term. This is a sub 3 or a sub 5. So if I turned this into a sub 5, that would give me a sub 5 plus 1. Like that's all I'm doing is I'm replacing the n with the term that I'm looking at, right? The 5th term. So by replacing this a sub 5 with the number 11, 5 plus 1 is 6, I would find the 6th term. 11 plus 2 is 13. So then I would do that again to find the 7th term and again to find the 8th term. It's just as easy as counting by 2. It's just as easy as counting by 2. This is the recursive formula. You just need to know how to write it. Okay? So now I want to write the explicit formula, which is y equals mx plus b. So the explicit formula requires you to, what is my common difference? 2. That's my slope. So y equals 2x. And what was my first term? 3. So let's talk about this. Remember that your first term is your initial value. Same thing. So that's just the explicit formula. Okay, let's move on to the next one and talk about a geometric sequence. So a geometric sequence, much like an exponential function, has a recursive formula. A sub n plus 1 equals b, which is your base, times a sub n. A sub n plus 1 equals b, which is your base, times the next term, okay? So let's look at this sequence right here. 6, 12, 24, 48, 96, dot, dot, dot. The first thing I need to do is find out what my common ratio or my base is. What am I multiplying by each time? Yeah, I'm multiplying by 2. So that's what my b is. So the recursive formula for this sequence is a to the n plus 1 equals 2 times a to the n. So if I wanted to know what the 1, 2, 3, 4, 5, if I wanted to know what the sixth term was, this is my fifth term. This is a sub 5. So a sub 5 plus 1, which is 6, is whatever 2 times the value of a sub 5 is. I'm using the fifth. The 5 is replacing the n. So 2 times 96. So the sixth term is 192. That's all that is doing. It just tells you the next term. So again, you guys need to know how to do this, and we're gonna practice this. Okay. The explicit formula is y equals a times b to the x, right? That's the exponential form. So what is my growth factor? Like when x is 0, if my first term is 6, what do you think this is going to look like? Well, my first term is 6, right? And my growth factor is 2 to the power of x. That's all you're going to do. But again, this is what your homework is going to ask for. So we're going to try it right here. So let's talk about what we need. We need to find the base for each one of these. We need to find the base for each one of these. And then we have to name the initial value. We need to write what a sub 1 is, okay? So let's look at example A. What am I, remember your base is your multiplier. What am I multiplying by each time to get the next term? My base here is 2. What is my first term? 5. So the recursive formula, a sub n plus 1 equals my base, which is 2 times a sub n. This is the recursive form. Well, what's the explicit form for that? Or actually, we don't have to do that. We're good. We're good right here. If we were to write this as an equation, what would I write? As an exponential function. Y equals, what's my first term? 5 to the power of x. Good job. Let's look at example B. What's my base or my multiplier? What am I multiplying each term by? 5. So the recursive formula, I have to say what the first term is. What is the first term in my sequence? 3. So a sub n plus 1 equals the base, the multiplier, times a sub n. This is the recursive function. What's the explicit formula going to be? Good job. Y equals 3 parentheses 5 to the power of x. Because it's an exponential function. Right? So remember that this is your multiplier. So if I know, so when x is 0, that gives me my first term, which is 3. When x is 1, that gives me my second term. 3 times 5 is 15. When x is 2, that gives me my third term. 2 times 5 to the second power is 25 times 3 is 75. This is just the exponential function. Like you're just taking the base and putting an x on it. Like that's the exponential formula. Let's try it again. So this one just asks us to take this information and write the recursive formula for it because it's already got the exponential or the explicit form. So what's the recursive form? Well, we need to find out what the base is. What's the base? What's my multiplier? Yeah, 0.2. What's my first term? 3. So A sub n plus 1 equals my multiplier, 0.2 times A sub n. This is the recursive part. Let's do it again. What is the base here? 5. What is my first term? So A sub n plus 1 equals what? What do I write? What goes next to 5 times A sub n? All right, this next part is kind of important. You have two ordered pairs. So we're going to write an exponential equation given two ordered pairs. So here's what I want you to think about. We have y equals a times b to the power of x. So if we could substitute in a y value and an x value, we could probably solve this, right? So what is something like, what is a value that I could put here for x of these ordered pairs that would tell me what a is? Let me show you what I mean. What if I use this ordered pair right here? Let's fill that in. So this is my y value and this is my x value. So 3 equals my initial value times b to the power of 0. But b to the power of 0 is what? 1. So this says 3 equals a times 1, which means that 3 is my initial value. Does that make sense how we did that? So now we're going to use the fact that we know what a is and use this x and y point. So we're going to rewrite y equals a times b to the power of x. But I know that a is 3. And I'm going to use this as my x coordinate and this is my y coordinate. So 6 equals b to the first power. I'm trying to figure out what b is. Well, b to the first power is just what? It's just b. So 6 equals 3 times b. Just solve for b. How would I solve for b? I didn't hear you. Say it again, McKinley, sorry. Yeah, divide both sides by 3. So b is 2. So your function is y equals your initial value, 3, times 2 to the power of x. This is the equation. So let's do it again. If you look at this function that we're writing on now, is it increasing or decreasing? It's decreasing. That means that multiplier b is going to be a what? A number less than 1, in between 0 and 1, right? So let's find the initial value first. Let's find a. Remember that I'm going to use y equals a times b to the power of x, but I'm going to let y equal 4, and I'm going to let x equal 0. And I do that because b to the 0 power is 1. Anything to the 0 power is 1. So that gives me 4 equals a times 1, which means 4 equals a. Is that making sense? You always want to use the y-intercept point first, okay? So now let's take that same y equals a times b to the power of x, but I'm going to replace the a with the number 4, and I'm going to replace the x with a 1 and the y with a 2. So instead of y equals, I'm going to say 2 equals 4 times b to the power of 1. Well, what is b to the first power? It's just b. So 2 equals 4 times b. Divide both sides by 4. And I find out that 1/2 equals b, right? Because 2 over 4 reduces to 1/2. So what is the exponential function? Yeah, good job. Okay. How am I doing on time? Okay, let's keep going. All right. So in 2011, the population in the US was approximately 312 million. So let's just write out what that looks like. 312 million looks like this. Okay. Suppose that in recent trends, the birth rate was 1.7% of the total population. Use A to the N to represent the population in the United States. So that's like this right here for right now. And A to the N plus 1 to represent any year after the 2011. So we're going to write a rule to show how to calculate the next year's population. So we need to figure out what our base is, what our multiplier is. Well, our multiplier is 1.7%. How do I turn that into a decimal? I move the decimal place over 2 times to the left. So B equals 0.017. That's my multiplier. However, if you think about this, if you were just kind of thinking about this, I'm going to take the population that I have right now. And to that, I'm going to add 1.7% of that population. So like this number times the 0.1017. So did you guys ever do sales tax? Okay. Well, if you want to know the sales tax of an item, like if it's 7% sales tax, you could take the price, $40, and multiply it by 7%, but then you'd have to add that back to the $40, right? Yeah, I'm going to write it up here. If I wanted to know how much something costs, so let's say that I have an item that costs $40. So it costs $40, but I have to pay 7% sales tax. So you could take $40 and multiply it by 0.07. That would tell you what 7% is. But whatever you get here, you would still have to add it back to the $40 to figure out what you were going to pay at the register. Does that make sense? So a way to do that is to just put a 1 in front of it. 1 times 40 adds that 40 back. Does that make sense? So that's what we're going to do to this multiplier. We're going to make it as 1.07. So that's going to take care of that addition portion. So really our multiplier is going to be 1.017. So our A to the N plus 1 equals 1.017 times A to the N. And that is your formula. What is the A to the N? Do you remember? Remember, A to the N right now is this number, 312 million. If I were to write this as an exponential equation, y equals my beginning value, 312 million, times my multiplier, 1.017 to the power of x. These are both the same. They work both the same way. Okay? Does that make sense? Remember, A to the N is starting with your initial value. We always know that our initial value, like when we say A to the N, that's really our initial value, which is I'm not going to write all those zeros again. Okay? So let's look at this table below. We have 3 questions to answer about this table. So this is the number of 10-minute periods. So it says, let's see, the table represents the number of bacteria in a cut after 10 minutes. So this is the number of 10-minute periods. And it says we have, let's see, a single bacteria. So when we first start, how much bacteria do we have? 1. Do I call it bacteria or bacterium? I don't know. I'm going to say 1 bacteria. And then how much do we add every 2 minutes? Every 2 minutes it grows by, so 1 times 2 is, that's my growth factor. And 2 times 2 is, And 4 times 2 is? And 8 times 2 is? And 16 times 2 is? And times 2 is? And times 2 is? 128. So this is in 10-minute increments. So this is really at 70 minutes, right? Because 7 times 10 is 70 minutes. Does that make sense? So at 70 minutes, I have 128 little bacteria in my hand, in my wound, okay? So the first question says, write a rule, and that rule is going to be our recursive. Write a rule that shows the number of bacteria in your hand at each 10-minute interval. So we have to tell what happened at the very beginning. So when I first started the first term, how many bacteria did I have? When I first started, I had 1 bacteria. So the recursive formula, a to the n plus 1 equals my growth rate. How much am I multiplying? What's my multiplier? 2 times a to the n. Now let's write an exponential equation for that. So my exponential equation starts off with y equals, what's my initial value? 1 times what's my growth rate? To the power of x. Okay. The last question says, find the number of bacteria after 140 minutes. So this is really saying let x equal what? Remember, we're counting x in 10-minute intervals. So we have to take 140 and divide it by 10, which is, so this is really saying let x equal 14. So we're going to use this function, y equals 1 times 2 to the power of 14 to figure out how many bacteria are in our hand after 140 minutes. So who's calculating that? 16,380 bacteria after 140 minutes. Okay. All right. I'm going to do like random problems of your homework. So go to number 3. I'm going to do number 3 with you. So you're going to do number 1 and number 2. I'll circle those in red. Maybe you can circle them on your paper, but I'm going to do number 3. So I have to determine if the table explains, like projects an exponential function and say why it does or why it does not. So let's look at example 3. First thing I want to check, are these all growing at the same increment? +1, +1, +1. Yes, check. Okay. What am I doing here? What's my multiplier? I'm multiplying by a -2, right? -1/2 times -2 gives me 1. 1 times -2 gives me -2. -2 times -2 gives me +4. So this is my multiplier. So it's exponential. The multiplier is -2. So did we say something about B? What did we say about B? Do you guys remember that we said the base has to be what? That's what we said. We said that the base has to be either in here or what? Or greater than 1. So we can't have a negative B. Does that make sense? So this is really not EXP because your base is a negative growth. We don't do that. We don't have a negative growth model. Okay? You'd have the multiplier on the outside be negative, but not on the inside. Next one. Because here's why. Remember exponential functions, like, so what would happen to that is your graph would be going up, down, up, down, up, down, up, down, right? Because you'd be going from positive to negative, positive to negative, positive to negative on your y-axis. And remember, graphs that are growing exponentially either go all the way up or all the way down, right? They like either increase exponentially or decrease exponentially. That would be jumping all over the place because your y's are going from positive to negative, okay? So it's not exponential because you have a negative base. Your B, your base, your factor cannot be negative. I want you to do number 5 and number 7. So I'm going to do number 4 and number 6. So we're going to write the recursive forms for each one of these. So the first thing I need to know is what my b is, and I need to know what my first term is. So what is my multiplier? Remember, b is my multiplier. What am I multiplying by each time? Yeah, 1/2. Good job. So b is 1/2. What is my first term? Yeah, 1/2. So a sub n plus 1 equals 1/2 times a sub n. This is the recursive equation. You have to include the first term in your recursive equation, and that's all you have to do. Just know what the multiplier is, okay? So number 5 is just like number 4. You just have to find the multiplier. Number 7 is going to be just like number 6, okay? So what is my multiplier or my base? 2. What is my first term? Well, the first term happens when x is 0, and that gives me my intercept, right? What's my intercept? 1. Good job. So a sub n plus 1 equals 2 times a sub n. All right. You are going to do number 9 and number 11. Number 11, the number is down here, but the graph is actually, or the table is actually on the next page. So I'm going to do number 8 and number 10 with you. Okay. So we're going to write the recursive form and the exponential form. Okay. So either way, we still need to find out what our base is. What is our growth model and our growth? And we need to find out the initial value. So what am I growing by each time? Yeah, I'm multiplying by 6. So my b is 6. What is my initial, my first term? 1. So someone give me the recursive form. Well, I'm going to write a sub 1 over the top of it equals 1. And what else? A sub, what's the recursive formula? N plus 1 equals your multiplier b times, yes, this is your recursive form. Let's put it in exponential. Y equals 1 times to the, perfect. Absolutely perfect. Okay. You're going to do number 9, which is much like number 8. I'm going to do number 10 for you. So what is my base? 2. What is my initial value? What is my initial value? 10. Yeah. So remember, your initial value is at 0 when x equals 0, because that's your y-intercept. So the recursive a sub n plus 1 equals 2 times a sub n. Yeah, it's just your base, your multiplier, what you're increasing by each time. And then the y exponential form is what? Yeah. Okay. So you're going to do number 9 and number 11. There's your table. I don't know if I wrote down that you're going to do number 12 or number 13. Okay, I'm going to do number 13 with you. You're going to do number 12. So you're going to do number 12, which is increasing. So your b is going to be a whole number. I'm going to do number 13, which is decreasing. So my b is going to be a fraction. So let's figure out what my initial value is first. A. We're just writing the exponential form for this. Just exponential, y equals. What is a? Meaning, where do I cross the y-axis? At 10. A equals 10. Well, let's figure out what happens when x is 1, right? Because that would just be b. When x is 1, that just is b, right? So when x is 1, I go to right here. What is that? I'm counting by 2s. So let's see, 2, 4. It's right in between 4 and 6. It's exactly in between 4 and 6. 5. So my exponential function is 10 times 5 to the power of x. So when you guys do number 12, you need to figure out what happens when x is 1, right? Because x, like when x is 1, that gives you b to the first power, which is b. And you need to figure out where you cross the y-axis, which is your a. Okay? All right. I'm going to do number, you're doing 15, 16. Okay, so I'm going to do number 14 with you. Oh, these are good problems. Okay. And this is the last. This is the last that we're doing. So you are going to eventually have to start solving exponential equations. These are two exponential equations. So here's the trick to this. First, you need to be sure that both sides of the equal sign have the same base. Okay? You need to make sure that both sides of the equal sign have the same base. And then if they do, once you get the same base, you set the exponents equal to each other. So let's look at number 14. I have 5 to the 3x power equals 5 to the negative 3 power. Do both of these have the same base? Yeah, so I'm going to drop those. I'm just going to ignore them. And I'm going to say that 3x equals negative 3. And I'm going to solve for x. So how do I solve for x here? Yeah, divide both sides by 3, and that means x equals negative 1. So let's check that. I'm going to plug in the fact that x is negative 1 and see if this comes out to be the right thing. Well, 3 times negative 1 is what? It's negative 3. Does 5 to the negative 3 power equal 5 to the negative 3 power? Yeah, so your solution is x equals negative 1. So for number 15, do they have the same base? Yes. So you're going to drop the bases and just work with the exponents. Number 16, do they have the same base? Yes. So you're going to drop the bases and just work with the exponents and solve for x. Number 17, they do not have the same bases. However, this is 1/1000th. So this is the same thing as this, 1 over 1,000. Is there a way that you could represent 1 over 1,000 as a power of 10? Well, it's a fraction. So that means that the exponent has to be negative. How many zeros are in that? So this is the same thing. This 0.001 is the same thing as 10 to the power of negative 3. Put it in your calculator. What is 10 to the negative 3 power? It'll tell you 0.001. So you have 10x equals 10 to the negative 3 power. Now I have the same base. I just drop the bases and I work with the exponents. X equals negative 3. I'm done. Okay. Got it? So for number 18, you're going to have to turn this into a power of 2. This is going to equal 2 to some power to solve it. Lorelai? 18 is one of the questions you have to do, yes. It's posted in Canvas, but yes, I'm just trying to tell you how to do it. For number 19, you're going to do number 19 as well. You're going to have to write this as a power of 6 to solve it. Okay? I'm going to do number 20 with you. So I have 16x to the x minus 1 power. What is another way to write 16? Four squared. So 4 to the second times x minus 1. So I have to still multiply by that exponent equals, can I write 64 as a power of 4? What is it? 4 to the third power, but remember it had an x on there. So now I have the same bases. I'm just going to work with the exponent factors. So my exponents are 2 times x minus 1 equals 3x. Well, I have to distribute. 2 times x minus 2 equals 3x. Subtract what? 2x from both sides. And I have negative 2 equals x. You know, I just don't believe that I need to check it. So 16 to the x is negative 2. So negative 2 minus 1 power equals 64 to the x is negative 2 power. Someone puts, what does this become? What is negative 2 minus 1? What is negative 2 minus 1? So someone put 16 to the power of negative 3 in their calculator, and someone put 64 to the power of negative 2 in their calculator. What do we get? What'd you get? Turn it into a fraction. Hit your fraction button. Okay. Did you do 64 to the negative 2 power? Or did you do 16 to the negative 3? Okay, so someone do 64 to the negative 2 power. Turn it into a fraction. If you're in decimals, hit the fraction button. It's the same. 1/4096. Okay. All right. So I'm going to go to Canvas really fast and